Let's go to our next topic. General topic would be for eigenvalues. Are you familiar with eigenvalues for the
Thank you, sir.
eigenvalue problem? Okay. So this is actually very useful when you are going to use matrices to formulate your uh, quantum mechanical problems. So Schrodinger equations can be, which is a wave equation, can be expressed as a eigenvalue problem. So we already know from your matrix algebra that for the eigenvalue problem, is of the form A minus lambda I times X equals 0, where A is your matrix n by n matrix, lambda are your eigenvalues, I is your identity matrix, and X is your eigenvector. Okay? This is coming from this form wherein your eigenvalue equation would look like this. Okay? So what does this mean? It means that this equation tells us that if you have a vector x and you multiply it with a matrix A, okay, it's the same way as magnifying or contracting your vector A, your vector x. So this lambda is a constant. Okay, there is a good illustration or visualization on how or why or what this equation uh, graphically looks like. Okay, but our focus for today is how to use this eigenvalue problem. Just remember, we used this in theoretical mechanics too when we use this as one of our approach to solve coupled oscillators. Okay, so remember your coupled oscillator. Let's say this is your coupled oscillator. Okay, you can refer to the detailed solution of this coupled oscillator. So let's say we have M1 and M2. Okay, and then this is connected by these three springs. Okay, where the three springs have the same spring constant K. Okay, so because we have two particles, these two particles will have two distinct position functions, x1 and x2, and this is what we're going to solve here. Okay, the equations of motion are as follows. Equation of motion for M1 would be M1 x1 double dot equals negative K x1 plus K x2 minus x1. And then for the second one, M2 x2 double dot, this is equal to negative K x2 minus x1 minus K x2. Okay, so if we're going to assume a solution, let's say of this form, say x equals a cosine omega t. So that means x double dot would be equal to a omega squared negative cosine omega t. Or simply negative omega squared x. Okay, so substituting this here, substituting let's say x in x1 and x2, and substituting x double dot to x1 double dot, okay, we'll end up with this matrix equation. simultaneous linear equation in terms of A. So this becomes, so equation number 1 becomes 2k over m1 minus omega squared a1 minus k over m1 a2 equals 0. And the second equation becomes negative k over m2 a2 plus 2k over m2 minus omega squared a2 equals 0. So sorry, this should be a1. Okay, so the matrix equation becomes the matrix equation becomes 2k over m1 minus omega squared, and this is minus k over m1. Here is negative k over m2, and then 2k over m2 minus omega squared times a1, a2 equals 0. Now we can see that this can now be written as an eigenvalue problem as follows. So this is 2k over m1 minus k over m1 negative k over m2 and 2k over m2 minus omega squared times 1, 0, 0, 1. And this is your a1 and a2 equals 0. So here, what we have is a is this one. Okay, this is a. Your x vector will be this one. This is your identity vector, identity matrix. And lastly, this is your lambda. So what we're actually solving here is the eigenvalues lambda. Okay, of course, you can solve this using the usual way by getting the determinants of the eigenvalue problem, wherein the solution would be can be determined by getting the determinant of a minus lambda I, and you equate it to 0. So from here, you'll get the eigenvalues lambda, and then from there you will be able to get the angular frequency of each of the oscillators. So that's why sometimes we call omega as our eigenfrequencies. Okay, so the solution to this, the solution to omega will now be equal to, so this is omega. If you're going to do the algebra, so omega squared would be equal to k over m2 plus k over m1 plus or minus k square root of m1 squared minus m1 m2 plus m2 squared. Okay, so by getting the determinant, you'll be able to get this one. So this is divided by m1 m2. Okay, so manually you should be able to determine the eigenvalues or the eigenfrequencies omega using this determinant. Now we can also do this by just using the eigenfunction. Okay, but in the meantime, let's have an example. So for example, let's say M1, M2 is equal to 40 kilograms. So that means your two oscillators have the same mass. And then the K would be 200 Newton per meter. Okay. Can somebody give me omega squared based on this equation? Sige, tawagin ko. Rain, can you calculate omega, please? And Christian, can you verify the omega squared? Can you use your calculators or MATLAB if you want?
Okay.
Okay, so Christian and Rain, can you compute? The others can also compute the two values of omega squared. So this is the...
Sir, alin po yung sa akin yung may equation?
This one.
Okay, okay.
Using these values. Rain, are you with us? Wala?
Yes po.
Okay, sige. Compute Rain. The others can also compute to verify them. Okay, now when you get the determinant, you will end up with this expression. Okay?
Sir, plus minus po ba yun? Dalawa yung value?
Oh, dalawang value. Kasi pag when you get the determinant, you'll end up with a quadratic equation in m squared and omega squared. So that will be omega to the fourth, etc., etc. So you'll end up with this equation. It's a long solution pag manual natin. Like 2 pages worth. Like this one. Up to kita. Mahaba. This is plus minus. Okay? Rain, may solution ka na?
Wait lang, sir. Nagkamali po ako.
15 and 5 po.
15 and 5, Christian, are you sure?
Apo.
How about you, Rain?
Wait.
So,
Yes po. Same.
okay, same. Okay, so that's 15 and 5. Okay, so one way to do it is just to compute for this and for this. This is actually 10 and this is 5. And then you have a plus and a minus, so that's 15 and 5. Now, how do we use this in MATLAB? Okay, so let's just use the command window na lang. Okay, so let's define A. So our A would be, sorry, can I? Okay, let me use this one. Okay, so A is this one. Okay, so let's define what K is. K is 200, and then M1 is 40, and M2 is 40. Okay, let's repeat that. Okay, and then let's use A. A would be 2 times K divided by M1. Then minus K over M1. Then negative K divided by M2. And then 2 times K divided by M2. This is your A matrix. And then we only need to use the eigen function. Eigen. So this is your solution to your eigenvalue problem. And then just type in our main matrix. When we enter this, we will have the two answers, 5 and 15. So 5 and 15 are the answers to your omega squared. So therefore, our omega would be square root of 5 and square root of 15.